discontinuous. So how do we solve it? I can say this two parts. Okay. For the being in this range A, okay, and the Q here on this is equal to 0. Okay, all right. So I solve two equations. I call the diffraction here, and this is a diffraction we call the W1, and this is a diffraction for this part B, another equation. Okay, this is solution W2. So for this two parts equation, okay, let's see the moment distribution. Okay. For x smaller than a, I have a R1 reaction, and this is a x. And x smaller than a, then we have a moment inside it. So the moment inside the mx is equal to what? R1x, right? Moment equal to R1x. Okay. So I can use a minus EI. W1 double prime equal to moment x equal to R1x to solve this. So I can have a minus EI W1 prime equal to half R1x squared plus C1. Okay, and integrate again, I can have a minus EI W1 equal to 6R1x cubic plus C1x plus C2. This is my equation 1. And okay, this equation I know W1 at 0 equal to 0, right? Because there's a hinge, there's no diffraction. So from this one, I can say C2 equal to 0. But this C1 still cannot determine. Because for x smaller than a, the only boundary condition I know is W1 equal to 0. Right? Then for the x larger than a, my moment is like 1. So this is a P, this is a A, and this is a X. And they here have a moment mx equal to 1, and this is R1. So the moment at this cross-section for x larger than A, at that cross-section, the moment is R1x minus P times x minus A. This is minus moment of P times x minus A. So this is my moment for the x larger than A, right? So for this, we have another governing equation is minus ER W2 double prime equal to moment R1x minus P x minus A. Okay, then I integrate twice. I can get a minus EI W prime 2 equal to have R1x squared minus have px squared plus pax. right? And plus C3. And furthermore, I have a minus, right here. Minus ER W2 equal to have R1x squared minus PX squared have PX squared plus PAX plus C3 and minus ER W2 equal to 6R1 x cubic minus 6P x cubic plus half PA x squared plus C3x plus C4. Okay. And for this one, I know W2 at L is equal to 0, equation 0. Right? So from here, I can have L. So have 6R1 L cubic minus 6P L cubic plus LP AL squared plus C3L plus C4 equal to 0. Okay? So here I have 2. Okay. So for W1, we already get 1 over ER minus W1 is 6 R1 x cubic plus R1x C1x, sorry, C1x. Because we know C2 are 0, right? So we have okay. Yeah. So we have one equation, and we have a C1, C3, C4, and we have 3 unknown. And we have, we need 3 equations. Okay, so this is 1. So we need another 2. What condition we need? We can have continuity condition, right? So this is an equation star, okay? We have an equation star as my boundary and another is what? Is W1 at A equal to W2 at A. They are using the same X, but different function. Okay? This one continuity, this diffraction is continuous at X for these 2 curves. Okay? And second, the third equation is W1 slope at A equal to W2 slope at A. So that means this is W1 and this is W2 and this is W1. At this X equal to A, we have this continuity and we have a slope continuity. Okay, so we have 3 equations. We can solve these 3 unknowns. Actually, we have 4 conditions. We already used 1. Okay. So we have 4 integration constants. Okay. Here, for example, my governing equation is highest is what? Is second derivative. So my boundary condition can only use to first derivative. I cannot use the moment at here 0. I cannot use because the moment is related to the second order derivative. Understand? Therefore, this is my second order. So my second order ODE. My boundary condition is highest order is first order. That means the slope. Okay. So I just can use a displacement and slope. Displacement and only displacement. Okay. I cannot use a moment. Moment here I cannot use. Because moment is related to the second order derivative. Okay. And here also I cannot use moment because of it. Okay. So for this problem, if I use second order, but if I use it, I solve the problem by fourth order. That will be more difficult. First order, we have 4 integration constants. 4 integration constants, right? So we need 8 conditions. What do we have? If you use the first order, you can use a moment here 0. Okay? Moment here 0, different 0. Moment 0, different 0. So 4, right? So we still have another 4 continuity condition. What? Diffraction continue, slow continue, shear continue, moment continue. So total difference. So here we just use second order. That will be easier. Okay, I only need to solve 4 unknowns. Okay, but this kind of way to solve this kind of discontinuous loading is too time consuming. So now we are going to teach a new method. Use a one expression and do integration directly. Okay, let's look at the half-range function. Okay, so okay. Any question? 问题？
就是需要到4个方程的那个东西是？
不要啊，你要的话很麻烦，要解8个未知数啊。
可是，
你看情形做嘛。当然我们能够用2阶 moment 的话是最快，只要几分2次就好。
只是像这个有点像是2句切很小段，那4个方程的那个是什么东西？有点难想象的实体或者是。
哦，4个方程就是你这个地方你还是解 EI。这段里面没有零，对，但是你4个方程你要解到这一段的位置的时候就麻烦，你这个 Q 你不会解，所以这就是为什么我们要用 set moment 就好 ，moment 就比较简单一点，懂我意思吗？Yeah, if you use the fourth derivative, you have to carry right out this kind of continuous loading is impossible. This discontinuous loading. So but use the moment is okay. We can get a moment, internal moment. Okay. So this is interesting. For being theory, EI, W, force